Okay, so first of all, I'd like to thank Jacob for inviting me to this. In fact, thank you for this whole seminar series. All the talks that I have attended have been really terrific. I think this is a really valuable contribution to the profession. And thanks everyone for coming. Okay, I'm going to start with a question. So imagine in front of you, you've got some physical system. I've got a glass of water whose physical state is incompletely known to you. And this is true of that glass of water. Imagine an angel appears and tells you an incredibly precise specification of the state. Okay, maybe not exact state, but it's a much better approximation than you had before. Here's a question that Shelley Goldstein has asked at several conferences and workshops and stuff. Has the system's entropy decreased when you gained that information? And sort of anecdotally, there are two sorts of answers that one tends to get. One is, and this tends to be more common among physicists, of course, one of the things we learned in the 20th century is there's a deep connection between entropy and information. And another common sort of ancestry is, don't be absurd. Entropy is patently an attribute of the physical microstate system, and that hasn't changed when you gained new information. Okay, what's going on here? Why are we getting two kinds of answers? And why do some people think that one of the sorts of answers is absurd? Well, I'm going to rephrase the question. Instead of talking about entropy, I'm going to talk about available energy. That was a phrase that the British physicists tend to use. They tend to talk about dissipation of energy or loss of available energy, even after Clausius coined the term entropy. They were sort of slow to pick up on the use of the term. So what is that? Well, suppose you have some physical system that you can manipulate in various ways. And you have one of the things you have available to you is a heat bath at some temperature T that you can use as a source or sink of heat. And you are tasked the system starts in a thermodynamic state A, and you are tasked with doing something, whatever you want to, and leaving it in another thermodynamic state B. What's the maximum work that can be extracted from the system? And the answer, okay, so this is more or less an elementary textbook thing. It's what you get if you get the maximum work if you do the thing reversibly, and the amount of work that you get is the difference between the initial state and final state of what Maxwell called available energy and Helmholtz called free energy, and as a result, we now call Helmholtz free energy. So it's just a difference between the internal energy and the and T times the entropy. So T delta S is going to be the amount of heat that is exchanged with the heat, where the heat bath and everything else is work. So, okay. So given that, I can rephrase Shelley's question in slightly different words. Reminder from the last slide, the available energy or Helmholtz free energy is internal energy minus T times S, the entropy of the system, and T is the temperature of the heat bath that you have available to you. It doesn't have to be the temperature that the system starts out at. Okay, so if we hold U and T fixed, then an entropy decrease is an available energy increase. So, and in the situation where the angel appears, neither the temperature of any available heat baths nor the internal energy of the system has changed. And so we can ask the same question. Did the entropy decrease as did its available energy increase? And then another way of saying that is, if you're tasked with making a transition that leaves it in some designated end state, has the amount of work that you can get increased? And the answer, I think, if you think about it, is very clear, is, well, maybe it has. If you have means available for manipulating the system that can exploit that knowledge that you've gained, then yes, the amount of work that you can get might have increased. If not, then it hasn't. Okay, why did I tell the story? Well, the moral of the story is this notion of available energy, which is a measure of how much work you can get out of the system or how much work you have to do to the system to achieve some state transition, is naturally relativized to both to means of manipulation available and information that one might have about the system. And if we want to retain the connection between entropy and available energy, then we have to accept the notion of entropy, on which entropy is defined relative to means of manipulating the system and information about the system. Nothing mysterious about this. Sometimes people express this in misleading ways. Sometimes people, even nowadays who are working in quantum thermodynamics, say things that suggest that this means entropy is subjective or anthropocentric, or Planck derided this notion as bringing anthropomorphic concepts into physics. I think that that's not the best way to put it, because something that's subjective, we tend to think it varies from person to person, things like matters of taste. And it doesn't matter who you are. This is defined in terms of some set of available manipulations and some information about the system. Okay, when you say things like this, philosophers tend to explode and object vehemently. And here's Karl Popper from a number of years ago. Instead of interpreting entropy as a measure of, I have to move the sideboard to read the whole quote. Okay, instead of interpreting entropy of a system as a measure of its objective state or disorder or randomness, many physicists interpret it as a measure of our own subjective state of ignorance of system. This interpretation leads to the absurd result that the molecules escape from our bottle because we do not know all about them, and because our ignorance is bound to increase unless our knowledge was perfect to begin with. I believe this is palpably absurd, and that hot air will continue to escape even if there's nobody in the quad to provide the necessary nescience. So there's Popper. Some of you may know this quote from David Albert's book, Time and Chance. Those of you who have heard David Albert speak should be hearing this in his voice. I'm sorry, I can't do an imitation. Can anybody seriously think that our merely being ignorant of the exact microconditions of thermodynamic systems plays some part in bringing it about, in making it the case that, say, milk dissolves in coffee? How could that be? What can all these guys have been up to? Okay, I think what's happening is that people are talking past each other. And I think what's going on is that there are actually two conceptions of what the science of thermodynamics is. One is something that I called in a paper that's now 2011, so now about a dozen years old, the Maxwellian view. That's the view that of thermodynamics is what physicists would now call a resource theory, maybe a family of resource theories. Not a theory of pure physics, but a theory of how agents with limited means of manipulating a system and limited access to information about its physical state can exploit its physical properties to achieve specified ends. That's how Maxwell and Kelvin and all the founders of thermodynamics thought about it. And this way of thinking about thermodynamics has recently experienced a revival among the people working in quantum thermodynamics. And if that's what you think thermodynamics is, the relation of thermodynamics to the underlying mechanics, be it classical mechanics or quantum mechanics, is much like the relation of quantum information theory to quantum mechanics. Quantum mechanics is the physical theory. Quantum mechanics doesn't know anything about Alice and Bob and what goals they have and what means of manipulation they do. But quantum information, it brings in tales of Alice and Bob and gives them tasks to do. And then you could do things like quantify various physical resources, how much they, like entanglement, how much they permit them to achieve certain tasks that they couldn't do without entanglement. So it's got physics in it, but it's bringing in some concepts extraneous to physics proper. Okay. On the Maxwellian view, thermodynamics is like that. Early in the 20th century, a view arose that thermodynamics can sever itself from its roots in those sort of considerations and become more like a traditional theory of physics. And on that view, which I call Planckian because the first person I know to clearly state it was Planck in a series of lectures that he gave at Columbia University in 1909, I think. Anyways, and then it's more like, you know, it's a theory of the macroscopic properties of matter in thermal equilibrium. And on this conception, the relation of thermodynamics to the underlying dynamics is presumably a case of reduction. And there's, of course, a lot of literature on how that reduction goes, if it does even work, and some consternation that it's not a very straightforward kind of thing. Okay. Now you can talk all day about thermodynamics and not really realize which conception somebody has in mind, but I think they are conceptually distinct. And in fact, the two conceptions of thermodynamics, the Maxwellian and Planckian, have different concepts of what counts as a thermodynamic state. So a thermodynamic state is specified by total energy and one or more variables, x1 through n. So for example, if it's a gas, then you can specify its state by internal energy and the volume of the container that it's in. What are these variables? Well, in Maxwellian variables, those are the thermodynamics, those are the manipulable variables. And it's via those variables that you're doing work on the system. So if it's a gas, changes in the volume counts as work done on or by the system. And in Planckian thermodynamics, these are characterized as extensive macro variables. And you can ask me how that might make a difference. You can ask me in the question period if you like. Okay. And I think one other, so, you know, I said I thought people were talking past each other. And I think to a certain extent that is true because they have in mind different conceptions of what thermodynamics is. You know, as I said, if you think of thermodynamics as a resource theory, if you think of entropy as a means of keeping track of availability of energy for doing work, then of course it's defined relative to a set of manipulations in a state of information. If you think entropy is supposed to be something that characterizes the physical state of a system, the maximum entropy state tells you what its equilibrium state is, then it seems absurd for it to be defined in terms of state of information. And I think another source of confusion is that when philosophers think about thermodynamics, most of the philosophical discussion isn't about the sorts of things that occupies most thermodynamic textbooks. When people talk about the thermodynamic arrow of time, for example, what they mean is the tendency of systems left themselves to equilibrate. And in fact, you often find as a gloss on the second law, the entropy of an isolated system does not decrease. Just a side note, if you're talking about thermodynamic entropy, that actually can't possibly be right because you need the second law in order to define thermodynamic entropy in the first place. So thermodynamic entropy is the integral of dq over t between two states along any reversible path. And it's the second law that tells you that that is actually well defined because the value won't change. It doesn't depend on which reversible path you use. Okay. All right. And the second law is often conflated with what Brown and Ufink in a classic paper called the minus first law or equilibrium principle. And it's kind of an interesting outlier when it comes to, they called it the minus first law because it's even more basic than the zeroth law. It's the principle that a isolated system has a tendency, will eventually come to a state of equilibrium that's a function only of its internal energy and the macroscopic variable, the and the constraints on it. It's kind of an outlier because it wasn't really until the 60s, a full century after people started talking about laws of thermodynamics, that anyone called it a law of thermodynamics. You would see principles like this stated, but no one called it a law of thermodynamics. And I think the case could be made that it doesn't actually belong to the laws of thermodynamics. It's a presupposition of thermodynamics. And well, we can talk about this if we want, but it's only a terminological thing. But another reason that this is different from the other laws of thermodynamics is, unlike the other laws of thermodynamics, you don't require a distinction between energy transfer as heat and energy transfer as work in order to state it. Okay. All right, so as I said a moment ago, if entropy is meant to have a relation to the availability of energy of our system doing work, and information is a resource, it's perfectly natural to have an entropy defined relative to a state of information. If, on the other hand, you're interested in explaining equilibration, you're thinking of entropy increase as the meaning of tracking a pro-Cayley equilibrium, then, as Popper and David Albert say, it is indeed palpably absurd to have it defined in terms of information. But, and this is the key point, no one has ever claimed otherwise. So Albert, in that quote that I had from Time and Chance, it ends with this rhetorical question: what could these guys have been up to? Well, I think what they were up to was Maxwellian thermodynamics. They weren't using entropy as a means of tracking progress towards equilibrium. Okay. So there are philosophers in the audience, so I need this warning or disclaimer. Please, please, please resist the temptation to write papers starting with this contrast of Maxwellian and Planckian dynamics and framing it as a debate about what thermodynamics really is, and consulting your intuitions or something like that in order to adjudicate the debate. I think that they're just both perfectly legitimate sciences, which for historical work are very closely related, but both have been called thermodynamics. And the same thing for entropy. There have been a proliferation of things that have been called entropy. They have various relations to each other. If someone offers you a concept that they call an entropy, ask what it is and isn't good for, and make sure that no one's using it in a context when it's not applicable. But it would be a waste of time to frame it as a debate about what entropy really is. Sometimes words have two meanings. And I've given this talk a couple times, and when the first time I gave this talk, I just assumed this was a cultural reference that was like Shakespeare was common to to Western culture. And I found actually that I've occasionally given this talk and found that nobody in the audience recognized it. So I don't care. All right. Now, one thing that might be in some of your minds, and this is an attitude that seems to be out there in a lot of the philosophical literature, is, okay, thermodynamic entropy defined in terms of heat and work, but we've got a better, purer concept, Boltzmann entropy, and we can replace thermodynamic entropy by Boltzmann entropy. And Planck, in fact, said that way back in 1909. He says, to have completed the emancipation of the entropy idea from the experimental art of man and the elevation of the second law thereby to a real principle was the scientific life's work of Ludwig Boltzmann. Briefly stated, it consisted in general of referring the idea of entropy back to the idea of probability. Boltzmann entropy, for those who aren't familiar with it, is you divide the available phase space for the system into macrostates. Macrostates are supposed to be ones that are a set of states that are macroscopically indistinguishable. And if the system is confined to some bounded area of phase space, any of those bounded volume of phase space, any of those macrostates will have a finite volume, and the Boltzmann entropy is proportional to the logarithm of the phase space volume. Okay, so question, can we replace the older idea of thermodynamic entropy with Boltzmann entropy? I think not. Each has a role to play that the other cannot. Even though typically they're almost exactly numerically equal. There are at least conceivable situations in which they come apart. And we'll be seeing in a moment, there are situations in which you can have a decrease of Boltzmann entropy without a decrease of thermodynamic entropy. So which goes to show that they are conceptually distinct, even if, for most purposes of calculation, you can interchange them. Okay, so this is a sort of example that has gotten some attention in the philosophical literature. David Albert in Time and Chance talks about it. Hamill Schenker in their book, Road to Maxwell Demon, talk about things like that. So imagine you've got a system whose phase space looks something like this. So these M1, M2, 3, M4, 5 are meant to be macrostates. Typically for a macroscopic object, we assume there's one macrostate that dominates the available phase space, in the sense of having a volume that just totally takes up almost all of the available phase space. But imagine you've got something like this, some kind of strange system like this, where you've got one largest macrostate, M1, and then 4 smaller ones, M2, M3, M4, 5, that are collectively, each one of them smaller, but collectively the same size as M1. And imagine that the evolution of the system is such that every point that starts out in M1 after a specified amount of time ends up in one of these other macrostates. Okay, so, and imagine this happens without any change of energy. It's an isolated system. Okay, so there's nothing in Hamiltonian dynamics that prohibits that. Hamiltonian dynamics says that phase space volume is conserved. That's okay, fine. The sum total of M2 through M5 has the same volume as M1 does. So it started out in a bigger state to a smaller macrostate. And that means that its Boltzmann entropy has decreased. So remember, Boltzmann entropy is proportional to the logarithm of the volume of the macrostate. Has the available energy increased? Has this decrease of Boltzmann entropy resulted in an increase of available energy? Okay. Well, it could be that if I give you a system in M2, there's a manipulation that you can perform that'll take it back to M1, extract heat from a reservoir and obtain work, and the same for M3, M4, and M5. However, it's provable not possible that there's a single operation that takes each one of those back to M1, obtaining work in each case. There's just no way. So if you want to obtain work, you're going to have to, if you know it's in one of those macrostates, you want to obtain work, then you're going to have to know which one it is in order to know what operation to apply. It's a consequence of Landauer's principle. As I construe it, there's been a lot of discussion in the philosophical literature about what Landauer's principle is. There is a version of it that is, in fact, a theorem of statistical thermodynamics. I'll talk about that later. Okay. So that means that in a case like this, where it goes into one of these other macrostates, but it's not predictable which, then the available energy has not increased. Has the thermodynamic entropy decreased? Well, thermodynamic entropy involves operations whose results are predictable. So you know, if it starts in a certain macrostate, you know what macrostate is going to end up in. And in cases like this, in which the Boltzmann entropy surely decreases, it's necessary that the final macrostate not be predictable from the initial macrostate. So I think what we have is a choice of how to extend the notion of thermodynamic entropy to cases like this. But if we want to retain the link between entropy and available energy, then we do have to say that in the absence of information about the final macrostate, there has been no entropy decrease. And on the Maxwellian conception of thermodynamics, that is in fact what we should say, because we want to retain the link between entropy and available energy. And if we say that, then this is a case in which Boltzmann entropy decreases, but thermodynamic entropy does not. Okay. So the system is one that assuredly decreases entropy. Should it count as a Maxwell's demon? Again, there's been discussion in the philosophical literature of this. Well, this classic paper, which if you haven't read, I recommend that you do, actually a pair of papers called Exercise 14 by Ehrman and Norton. They distinguish between straight and embellished violations of the second law of thermodynamics. A straight violation decreases the entropy of a diabatically isolated system without any compensatory increase of entropy elsewhere. And embellished violation exploits such decreases in entropy reliably to provide work. So you could use it in an engine that works in a cycle, for example. Similarly, David Wallace has distinguished between two types of demons. A demon of the first kind decreases some kind of coarse-grained entropy. Demon of the second time violates the cardinal bound on efficiency of a heat exchange over a repeated cycle that restores the state of the demon plus any auxiliary system utilized to its original thermodynamic state. I think these are more or less the same distinction. Demons of the first kind, the best they can do is a straight violation that would require a demon of the second time to effect a embellished violation. And I think really, it's only demons of the second time capable of performing embellished violations that are a threat to the second law of thermodynamics. So if you think that the physical possibility of a demon is supposed to be a threat to the second law of thermodynamics, then we should only call demons of the second time demons. And this sort of evolution that you're talking about, we're talking about, that assuredly reduces Boltzmann entropy, is going to be a demon of the first kind, effecting a straight violation. Okay. Switching gears a bit, since we've got some philosophers in the audience. I think there's been a lot of confusion in the literature about the relations of Gibbs and von Neumann entropies to thermodynamic entropy. So I'm going to say a few words about that. Okay, one possible statement of the second law is there is a state function S with a property that if a system passes from a state A to a state B while exchanging heats with heat reservoirs at temperatures Ti, heats Qi, sorry, at heat reservoirs with temperatures Ti, counting heat into the system is positive and out of the system is negative, then the sum of Qi over Ti over that transition is less than or equal to the difference in S. And if we can connect the two states reversibly, meaning that we can go from A to B and then B back to A such that the sum of Qi over Ti is equal to 0 over the whole thing, then that will uniquely define the entropy difference between those two states. Also, if we can approximate reversibility as closely as we like, that uniquely defines the entropy difference. Okay, so that's thermodynamic entropy. Now we want to go to statistical mechanics. Statistical mechanics, unlike thermodynamics, takes into account the fact that macroscopic bodies are conceived of enormously systems of an enormously huge number of degrees of freedom. And one thing that when people first started thinking about this realized fairly early on, and as Maxwell was the first to state clearly, kinetic theory of heat entails that the second law of thermodynamics was originally conceived can't be strictly true. If you could have two systems in thermal contact with each other and energy spontaneously pass from the cooler to the hotter just because of fluctuations of molecular motion. Okay, but on a macroscopic scale, macroscopic fluctuations of that are expected to be really rare. So the response then, which what physicists say is, What the original version of the second law deemed impossible, we should regard as improbable. And that is, in fact, what people in the 19th century said. So Maxwell, perhaps the first one, but Gibbs and Boltzmann and pretty much everybody who was working on the things eventually came around to that view. So we're going to have to, we ought to, if we want to talk about things being probable or improbable, let's introduce probability distributions over the state, space, or system. For what purposes, that raises the question of what those probability distributions are, what they mean. We can postpone that to the discussion. For the purposes of the theorems, it's not going to matter too much. But just sort of warning, because physicists are often told that talk of probability is an implicit reference to some large collection, either actual or hypothetical, of similar systems. That's in the philosophy of probability, that's a conception of probability often called frequentism. And if you read the literature on philosophy of probability, there seems to be more or less consensus that frequentism is an untenable view. So I just want to, whatever probability means, we're not making implicit reference to an actual or hypothetical collective. We're talking about probability of states of a single system. Okay, so I want to introduce concept that I think is central to statistical thermodynamics, a canonical distribution. That's a distribution on phase space whose density function is given is that proportional e to the minus beta h, where h is a Hamiltonian system and beta is the inverse temperature 1 over kT. And I think what I'm going to call the fundamental assumption of statistical thermodynamics is that when you're calculating probabilities of results of interactions with heat reservoir, go ahead and use a canonical distribution. And the reason on the slide I say you can't do better than to use it. And the reason I'm saying that is that you might have some knowledge about the detailed microstate of the system that's irrelevant to its further interactions with system because it's been so buried with other systems, it's been so buried. So you might as well use a canonical distribution. And so the idea is there's something about the process of equilibration that effaces information that you used to have, renders it useless or inapplicable, so that you can't do better than use a canonical distribution uncorrelated with the states of other things. So there might be correlations between the state of your heat bath and things it's interacted with, but they might be buried so deep in the state of the system that you can pretty much ignore them. Okay. If you accept that, then there's a version of the second law, probabilistic version of the second law, which is in fact a theorem, a not too difficult theorem. And the theorem is there is a functional S of probability distributions such that if a system, I have to move my sidebar again, sorry. System with initial probability in row A, or system starts out with initial probability distribution row A and ends up with distribution row B, interacting with heat reservoirs at temperature Ti. Then if we look at, because we're dealing with probabilities, the exact values of the heat exchange won't necessarily be predictable, but we can look at the expectation values and they're going to satisfy that. With respect to that function, and with equality if the process is reversible. Okay, as I said, if you assume that, so the fundamental assumption is an assumption about the appropriate probability distribution for use with those heat reservoirs, if you accept that, this is actually a theorem. And so this is word for word the same as the statement of the second law I had on the slide a few slides back, with exceptions that we have replaced thermodynamic states with probability distributions, and we have replaced actual heat exchanges with expectation values. Now, sometimes people get confused by this. When we're talking about the expectation values, sometimes people think, okay, you're assuming that the actual value is going to be given by that heat expectation value. And the answer is no, we are not. But so why are we interested in expectation values? Well, Szilard said in a paper from the 1920s that if you accept that the original version of the second law can't be strictly true, that we have to replace it with a probabilistic version, the second law is going to be like the theorems about the impossibility of a gambling system. So that if you're trying to play a game against nature and continuously extract more work than the Carnot bound, then no matter what you're going to do, the expectation value of the work you extract isn't going to exceed the Carnot bound. So in the long run, you cannot reliably win this game. All right. Okay. Moving towards talking about Landauer's principle. Okay, so from the previous slide, for any process, we have this relation between expectation values of heat exchanges with reservoirs and differences in Gibbs or von Neumann entropy, depending on whether we're talking about classical or quantum systems. And it's reversible if that's equality. So let's say it's dissipatory if it's not reversible, if that's a strict inequality. And we'll define the dissipation as the difference between the values of sum over I of expectation value Qi over Ti and the difference in entropy. So that's going to be 0 for a reversible process. That's going to be positive for any other process. So that's a measure of how far something is from being reversible. Okay. So example of a dissipatory process is free expansion. If I did it reversibly, then I would connect the thing to a heat reservoir at temperature the same as the gas and slowly expand it, getting work. If I have a gas that's confined to a partition and remove the partition, just let it expand freely, there's a lost opportunity to gain work, and it's dissipatory. So no heat in the free expansion, but if we were to do it reversibly, it would involve heat into and work out of the system, and so the dissipation as defined on the previous slide is positive. Okay, so suppose getting to the Landauer theory. Suppose you have some process that takes each of a set of distinguishable initial states, and remember, states here means probability distributions over the state of the system. Distinguishable means that they have measure 0 overlap in their supports. Suppose you have a process that takes each of a set of distinguishable states to the same final state, same final probability distribution. And the theorem is that no process can do that reversibly for all the initial states. Right. And in fact, there's a bound on the dissipations. So if delta I is the dissipation, as it's defined on 2 slides ago, associated with the transition that takes AI to B, it follows from the probabilistic version of the second law that these dissipations must satisfy this inequality. I've got a paper that's forthcoming in BJPS, which is available on their website. Also, a typo-free version is available on the PhilSci archive. If you want the proof, you can look at it. And the consequences of that, I don't claim that this is supposed to be immediately obvious, but this is a consequence of that, is that the average dissipation over each one of those transitions is greater than or equal to K log N. If you just want to visualize the Landauer band for 2 initial states, which is the ones that you most talked about, so the allowed if here the x-axis, the horizontal axis is dissipation associated with transition from A1 to B, the vertical axis is dissipation associated with B1, or A2 to B, and the gray area is the allowed values of the pair of dissipations by a single process. So you can make one of them as small as you want at the cost of making the other one higher. Okay. Going back to the Ehrman and Norton exercise 14 paper that I alluded to a bit earlier. Some of the literature on Maxwell's demons seems to suggest that Landauer's principle is invoked as an independent principle to rescue the second law from supposed threats. And I think that that's just a misunderstanding. Ehrman and Norton distinguished what they call between sound and profound exorcisms of the Maxwell's demon. A sound exorcism presumes the second law holds. A profound exorcism invokes hitherto and neglected and novel physical principles. And as I said a moment ago, Landauer's principle is a consequence of the probabilistic version of the second law. If you're arguing the demon is impossible, sorry, there's a typo, shit. If you're arguing the demon is impossible on the basis of Landauer's principle, then you're on the sound horn dilemma. And by this point, even though the earlier literature on thermodynamics of computation was kind of unclear on this, I think by now it's more or less uncontroversial. So Bennett, for example, in 2003, said it is Landauer's principle is indeed a straightforward consequence or restatement of the second law. Okay, but nevertheless, it has. Bennett says it still has considerable pedagogic and explanatory power. And what he means by that is that if you're analyzing some system that is meant to be a Maxwell's demon, meant to consistently and reliably violate the second law, meant to be a demon of the second kind that affects embellished violations of the second law, then if the you should remember that the demon is supposed to act in a cycle, and that would mean resetting whatever state that it ended up in as a consequence of its actions back to the initial state. And Landauer's principle would conserve a sort of reminder that you need to take care of dissipation, consider dissipation associated with that. And that's why it has pedagogic power. I'm not quite sure what he means by explanatory power, but okay. So summing up, there are two distinct but related sorts of investigations go by name thermodynamics, Maxwellian and Planckian. I think we should not ask which of these possesses the true essence of thermodynamics. And I'm planning on writing a book in which I argue that many of the philosophical puzzles associated with thermodynamics stem from not distinguishing between the two. There is a plethora of distinct concepts that go by the name of entropy. Please do not ask which of these possesses the true entropy, but ask what each is and isn't useful for. And in this talk, for the sake of time, I sort of skated over some details, but if you're interested, I've been writing in the past few years about these things. I have an article in the Oxford Research Encyclopedia of Physics that came out last November. An article in Foundation of Physics came out a couple of years ago. There's the BJPS article that I alluded to, and there's a paper which is going to be a chapter of that book on the relations of laws of thermodynamics to statistical mechanics on the PhilSci archive. And I think I came in less than 50 minutes, which is good because I was hoping we could get lots of discussions. So that is all I have to say. Thank you, everyone, for listening.
All right, so the first hand I have is from Gabriella. Please go ahead.
So first of all, thanks for the talk. I just wanted to say that this confusion about people talking past each other is also there in the physics community, and I've assisted it many times. And I wish you have better luck than what I had trying to sort of disentangle these issues. One thing that I want a little bit to push back, though, is the quote that it's absurd to use information to track equilibrium, because that's something that it's done. I mean, the only problem, of course, that it's not agent information at that point. It's essentially the information that is being lost by the noise. I mean, you have a process that is scrambling things around. So your initial setup, your initial information about the system gets lost. And you can also understand determinism and reversibility in terms of information transfer, in the sense that determinism means that the information that you have, the initial information that you have is preserved by the system, because you can use it to identify the final state, and reversibility is sort of the opposite way. So yeah, so a comment on that. I think that it can be used, with this idea that it's not the information about from the agent.
Okay, so you're talking about information that you had, right? And so people like Popper and David Albert say, well, who's you? Because, what they would say is this process of equilibration is going on, was, whether there are people around who know anything about the system or not, or, what's going on before there were any knowers at all in the world. So so I might be sympathetic to what you're saying, but I would like to hear a little bit more about what it is you're saying. When you say, when you say information that you have, right? So, who's you? Yeah.
Well, at that point, it's basically the information that has been encoded in the state of the system, regardless of how it was, right? So it's not me specifically. Like at the beginning, I have a microstate of the system, and then at some point that the microstate is subjected to disturbances from the outside, and so there is going to be an objective correlation between the what information was encoded initially in the system and what.
Right. So you're imagining a system that is subject to perturbations from the outside, and then basically information that someone might have had about the state of the system at the beginning becomes lost, becomes irrelevant to the later. I think that there is something to that, and there is a way of talking about equilibration in those kinds of terms, which could be defended against the Popper-Albert type objections. But it has to do with not what anyone happens to know or not know, but what someone could have known about the system, like right, because it is true that if I start with, say, some state of information about a system and subject to the sort of situation you're talking about, then what you knew about the system eventually becomes useless to future predictions, and if we're right about the fundamental postulate, then eventually the best you can do is use the canonical distribution. Even though, if you think everything's deterministic, then okay, now the initial state of your system has turned into initial state of system plus environment, but that doesn't matter, because that's useless for making predictions about how that system's going to react to further interactions. Yeah, so so I actually do think that a case can be made that for using information theory concepts in discussion of equilibration, that sidesteps those kind of objections that Popper and Albert were raising. Yeah. Who's next?
All right, thanks, Gabriella. So next we have Roman.
Hello, nice presentation, very interesting.
Thank you.
So I have a question. You are using quite a lot the concept of information, and it is obviously related to entropy. How do you define information? it is Shannon definition. It is something subjective. It is something that Popper had in mind in three word, ideas. What is it in your view that makes information controlling factor or factor in entropy, and what is information per se for you?
Okay, so I did sort of like when I sort of phrased the initial thing, I said it does make sense to talk about entropy defined relative to a state of information or a state of knowledge. But in the actual theorems, no notion of information actually occurs. The word doesn't occur. And so what I was basically assuming was you can, if you have imperfect knowledge about the system, then we can represent what you know about the system by a probability distribution over its state space. Notion of quantifying information was not necessary, though of course the theorem that the functional that plays the role of entropy is the probabilistic role of entropy is the Gibbs entropy or the von Neumann entropy, which is of course formally similar to Shannon entropy, but I wasn't intending to use information as a central technical term.
So it is just let's say metaphorical use of concept of information. This
not metaphorical. I mean, I think that if I know something about a system that is reflected in what states I think are probable and which are improbable, I don't think, but it's not necessary to use information as a technical term.
So
I'm not saying okay, and I'm not saying you can't. Okay.
No, I'm not attacking you. No. I'm just trying.
Right.
I'm trying to learn from you. So last question. I'm not extending this. So information for you is your subjective, quote unquote, knowledge about the state of the physical state of the system.
If you're talking about on the Maxwellian view, if you're talking about what you can do to a system to achieve work or something like that, then if you're going to have to make a choice of which operations to do, then that does have to be your state of belief, yes, of the agent. So right. So there's agent, there's conceptions of agency all over the place in the Maxwellian view.
Very short last question. What kind of food you buy for the cat? Okay, no answer. Just kidding.
Leo is an elderly cat, and he's had urinary tract discussions. So I buy Royal Canyon urinary SO for Leo, and I must say that's a question that no one has ever asked me before in a seminar, even though Leo has attended several talks during the Zoom era.
Certainly on physics seminar, nobody asking those questions. Thank you very much. Sorry to take your time. Thank you.
Thanks so much, Roman. Next I have Jens. Please go ahead.
Hey, thanks. That was great. I enjoyed it a lot. Also the cat. I wanted to ask about what you said about the failure of reduction of thermodynamics to statistical mechanics. It was on the slide where, it changes from one macro state to one of the five, and we don't know which. So I just wanted to ask about the presuppositions here that lead to the failure of the reduction. So,
I don't think I said failure of reduction.
Oh, I thought you the example was to show that thermodynamics or that the thermodynamic entropy no longer reduces to Boltzmann entropy. That was
Thermodynamic
get this
entropy and
wrong?
Boltzmann entropy are distinct. Yes.
and right.
And,
And this example,
and in some cases, you could have a reduction in Boltzmann entropy without a reduction in thermodynamic entropy.
sorry,
Right.
sorry, I meant failure of theoretical reduction, not failure of reduction in entropy. Sorry, there was two senses of reduction here, Floyd. I meant, yeah.
I'm sorry.
Well,
I'm pretty sure. Okay, if I ever said failure of reduction, it was a slip. On the Maxwellian view, you wouldn't expect a reductive relation. On the Planckian view, you would expect a reductive relation between thermodynamics and statistical mechanics, and depending on how liberal you want to be with the notion of reduction, I think that that's a sensible project. But I think that what I said is there's some consternation in the literature because the reduction is anything but straightforward. Yeah.
Right. Yeah. Good. So that was on
but on the Maxwellian view, it's just seems like a category mistake to say that thermodynamics reduces statistical mechanics.
Right. I mean, you could. Good. So I mean that already clarifies part of it because I wasn't sure whether the troubles with reduction only occur on your view, on the Maxwellian view, but it seems that seems to be the case. But even on the Maxwellian view, I mean, what are the prospects for kind of devising like a subjective analog of Boltzmann entropy that kind of mirrors the Maxwellian view of thermodynamic entropy? Like, we could in the I don't know, I haven't thought super deeply about this, but in the example that we discussed, could we have a notion of Boltzmann entropy that is not sensitive to macrostates as individuated by the available mechanisms, but rather individuated by the available mechanisms that we can also apply given our knowledge?
So if you're looking for a statistical mechanical analog of thermodynamic entropy,
On the Maxwellian view, yes.
On the Maxwellian view, I think that the analog is, in the classical case, Gibbs entropy, and in the quantum case, von Neumann entropy, and with a qualification that we're not necessarily talking about the fine-grained Gibbs or von Neumann entropy. So, and the reason I'm saying that is, think of the sort of stock example in the literature. You imagine gas initially confined to half of a receptacle, and you pull out the partition, and you consider a fictitious case in which it evolves entirely in isolation, so no disturbance whatsoever from the outside. Yeah. For isolated evolution, von Neumann or Gibbs entropy is conserved, and it doesn't increase. Okay. But now, so imagine a kind of situation like that where the thing has relaxed to an equilibrium, and now put it in contact with a heat bath at the same temperature. No change whatsoever in its observable macroscopic behavior, or and no change in what we can do with it, but big change in the von Neumann or Gibbs entropy. Right? And so that probability distribution that you get from plausibly, that probability distribution which you get from starting with something that's in half the box and letting it evolve, that's still has a support in a very small region of the phase space, and say the canonical distribution at the same temperature are thermodynamically equivalent in the sense that any work or any manipulation you do, the system is going to any work you can get out of it by any manipulation you do, the system is going to respond in pretty much the same way. And so in the Foundations of Physics paper that on my last slide from 2020, I talk about probability distributions being thermodynamically equivalent in the sense that probabilities of outcomes of feasible manipulations are the same. And so that for any probability distribution, there'll be a class of thermodynamic equivalent ones, and the thing that is the analog of entropy for that is the Gibbs entropy, the maximum Gibbs entropy among that class. Right.
I see.
And
Okay.
so basically what you're doing is, in effect, coarse graining the distribution. And people have derided that as an ad hoc move, but it's not. If you think about what you want on the Maxwellian view, what you want a statistical mechanical entropy to do, that is what you end up, the thing that does that work.
Okay, yeah, that's
So
helpful.
there's more details in the paper. But.
Okay, yeah, yeah, I'll be sure to check that out, and also the others that you link. But just in the one example that you had in the talk, the other thought is just that the a probability distribution that we have on the Gibbsian view, that just gets spread over all of the 4 boxes that the system it incorporates our ignorance about what box the system ends up in. Okay, great. Thanks.
Right, thank you very much. Next hand I have is from Elias. Elias, please go ahead.
Thanks. Hi, Wayne. Thanks for the talk.
Hi, good to see you. It's been too long.
Yeah, too long. Very interesting and very useful. So my question is the following. Suppose that I'm interested in explaining why systems equilibrate, or in explaining the thermodynamic arrow of time or something like that. Then I must only consider the Planckian framework and Boltzmann entropy, or is there anything that the Maxwellian framework can tell me about those sorts of questions?
Yeah, I actually think, and this is purely a terminological thing, that we should regard explanation of equilibrium as not part of thermodynamics. I made this remark that this what Brown and Newton call the minus first law of thermodynamics, the equilibration principle, perhaps should not be regarded as a law of thermodynamics. And I have a paper that came out a couple of years ago in the Statistical Mechanics and Explanation volume edited by Valliore, where I argue that there is a case for not including that as part of thermodynamics. And the reason is that thermodynamics, as originally conceived, is the science of interconvertibility of work and heat. That's where, by the way, this is for everybody out there. There's a sort of folk etymology of the term thermodynamics, according to which it should mean science of how heat moves around or something like that, because we think of dynamics as dynamical laws of evolution or stuff like that. But the term thermodynamics comes from the Greek words for heat and power, and it is chosen to be the science of heat and work, right? And all zeroth, first, second, and third laws require a distinction between energy transfer, heat, and work, but if you're talking about an isolated system equilibrating, you're not talking about its exchanges with energy. So, if you aren't using the concepts of heat and work, then I think that you're outside the realm of thermodynamics. So, what should we use and to track? So, I think study of equilibration is actually a distinct study from thermodynamics, though it's presupposed by thermodynamics, it's presupposed that the things thermalize when left to themselves. What should we use? Well, I think that it could be Boltzmann entropy. It could be something else. I think that one should really look at and it might vary from case to case. You use, whatever tools are useful for that. But I don't think it has to be an entropy. You might conceivably define some quantity that tends to increase during the process of equilibration, and it's not an entropy.
Again, follow-up question. Do you think that explaining with whatever tools you can the minus first law would answer all the mysteries about the thermodynamic arrow, like all the questions that philosophers are interested in?
Well,
would
the
be
philosophers
answered
tend to
by
be
answering by
interested
doing
in
that?
what they call the thermodynamic arrow of time, which I don't think is actually should be thought of as we should call it the equilibration arrow of time. So that's actually where most the literature on what's called the philosophy of thermodynamics is almost entirely focused on that arrow of time issues, which I actually don't think belong to thermodynamics at all. So I mentioned I'm going to write a book on philosophy of thermodynamics, and when I send the prospectus to publishers, I'm going to say this is the first treatise on the philosophy of thermodynamics, because everyone else has been talking about equilibration. But a lot of a lot of the big questions have to do with arrow of time kinds of things, and that has to do with the process of equilibration. Or actually, I think we need another word than equilibration, because there are systems that don't go to an equilibrium state. Right? So, think of a gas in a box, right? No matter what state it's in, you expect it to achieve a uniform temperature and pressure, right? Now, just take a blob of gas in free space, not in a box. We expect that to just expand forever and get more and more diffuse. And explaining the tendency of the gas in the box to equilibrate and the tendency of the gas in free space to just spread out ought to have they're the same sort of process, even though one system doesn't have an equilibrium state. Right? Mm-hmm. So that I think, I have thoughts about how one ought to explain that, but maybe we should go to other questions first, because
all right,
it takes us a bit far afield.
Thanks, Wayne. Very, very, very interesting.
Thanks, Elias. Stephen, you're next.
Hi, thanks very much for the talk. I enjoyed it a lot. I think this is one of many cases where people are talking past each other by using the same words and using slightly different things by them. I'm trying to sort of wrap my head around what the relation is between these two formulations, these two views of thermodynamics. And the way that I'm thinking of it, and I'm curious whether this is sort of the right way to think of it, or if this is, naive or on the wrong track, is that, if all possible agents have similar or roughly the same constraints on the information available to them, then, the properties of a system that are dependent on agent information become sort of de facto objective properties of the system. So I guess my first question is just, am I thinking of that the right way?
Yeah, I think that's the reason why, in fact, I think that 20th century textbooks tend to blend the two conceptions, right? And the reason I think that it's usually, it can go unnoticed that on the Maxwellian conception, entropy is defined relative to a manipulable variable, so something like that, is that implicitly in the background some set of possible manipulations that is taken for granted, and it's also I think implicitly taken for granted that any macroscopically observable distinction between two states one could potentially manipulate for exploiting work. So there's an I just want to illustrate what I said. So one way to illustrate the distinction between the two conceptions is to think back to this example that got some discussion among Maxwell and Gibbs, etc. So imagine you've got, and it ends up in textbooks. So imagine you've got a gas with a partition you've got a container with a partition in it, and you've got gas of same temperature and pressure on each side. Pull the partition out and let it settle down. Has there been an entropy increase or not? Well, the standard answer is if the samples and gas on the other sides of the partition are the same kind of gas, no entropy increase, because initial and final thermodynamic states are the same. But if they're different, say on one side we've got oxygen, on the other side we've got nitrogen, then there is a entropy of mixing, and then you can calculate it. Okay, so question is, what counts as same or different? And on the Maxwellian connection, you're going to conception, you ask, when those two things interdiffused in each other, was there lost opportunity to do work? And so if it's oxygen and nitrogen, if you've got some way of differentially manipulating oxygen and nitrogen, they have different masses, then if you're clever enough, you could probably think of some way to achieve that diffusion reversibly and extract work. But then on the Planckian conception, you would ask, okay, are they macroscopically distinct in the sense of, is there a measurable difference between them? And in theory, those things could come apart. You can imagine a measurable difference that you don't have the ability to exploit. Like Tim Maudlin in some discussions has said, imagine a red gas and a blue gas, right? And then they mix to become a purple gas. And he's assuming that you can't differentially manipulate the red gas and the blue gas, right? But they look different. Okay. Well, if you can't, then on the Maxwellian, if you can't differentially manipulate the red and the blue gas, then on the Maxwellian conception, there has not been an entropy increase because you haven't lost to manipulate. And on the Planckian conception, there is, because they're macroscopically distinct. Now, of course, red and blue means different electronic properties, and someone more clever than I would probably be able to figure out a way to differentially manipulate them and get work out of that diffusion. So yeah, so for most purposes, it doesn't matter. Yeah, which conception you're talking about. And the same with for most purposes, differences in Boltzmann entropy and differences in thermodynamic entropies are going to be so close to the same that it doesn't matter.
Right. So just to quickly follow up, so where my mind kind of goes is whether whether those implicit constraints on that we're assuming that allow us to in physics textbooks treat them equivalently can be made precise. And I get what I'm particularly thinking is, I can't really conceive of an agent that has radically different kinds of constraints on the information that it can get out of a system. But I don't know that there's anything in statistical mechanics that's telling me that such an agent should not be possible. Is that just a matter then of going to the whatever underlying dynamical theory is behind the statistical mechanics, or is there some way of within within just the statistical mechanics of making those constraints more precise and saying this kind of agent could not exist?
Right. Yeah, I like the way you're thinking, and I don't know a way of making this precise. So I'd like to if I can, but here's what I think about this. So Maxwell imagined a being that could manipulate individual molecules, right? And what Maxwell said is that his demon could do what is at present impossible for us. I think, this is 19th century age of technological optimism. I think maybe he was imagining we might be able to someday build machines that could do what this demon could do. Could there be things that we would count as agents that would have very different manipulability property than us? I think that here's a kind of a hand-waving argument that a lot of what applies to us is going to apply to anything out there that could act as an agent. And here's why. In his book, What is Life?, Schrödinger asks a seemingly nonsensical question, which is, why are atoms so small? And the reason that's seemingly nonsensical is that small is a matter of scale. Like they're small on the scale of meters and feet. They're of order 1 on the atomic units, and they're huge on the order of a Planck scale, right? But here's a way to make a sensible question about this. Why are they small relative to the sorts of scales that we typically deal with the world? And another way of saying that is, why are atoms, why are we so big compared to atoms? And plausibly the answer is that anything like us that could have agency in the world will have to deal on scales where things are more or less predictable. And he had already earlier argued in the book that all the regularities we see in the world are statistical regularities of having to do with aggregate properties of large numbers of individually unpredictable molecular motions. And so if that's right, then anything that could reliably manipulate things or have things that we could think of as states of knowledge and have any sort of agency would have to be dealing with things on a scale where you're dealing with things at a macro level and relying on statistical regularities of aggregate properties of large numbers of molecules. Right. And I think there's something right about that. I don't know how to make that precise. But, and this is, I've had discussions with several people with this before, because, Carlo Rovelli, as you may know, has this notion that entropy is something relative to the way it's something that interacts with it. So something might have one entropy relative to one system and another entropy relative to another system, and that interacts differently. And you might ask, well, could there be agents that attribute very radically different entropies to things than we do? And plausibly the answer is no, that any agents would have similar limitations of manipulability than we do. Now, there's a qualification, because like when people actually compute entropy tables, like you can go. There used to be books. I guess they're online now. There are books where you can calculate where they've actually measured entropy of various states of various things. You have the decision of what variables to count. So do we count? If you're dealing with a gas, we do make a distinction between oxygen and nitrogen. Do we also want to make a distinction between various isotopes of oxygen? So with a gas with gases with different proportions of different isotopes have different entropies. And the answer, I think, depends on how are you going to manipulate them. If you're only going to dealing with chemical interactions, then the differences between isotopes doesn't matter. If you're doing mass spectrography, then presumably it does. So
Right, makes sense. Thanks.
Thanks, Stephen. I have an anonymous question in the chat.
Okay.
Did the fact that Boltzmann abandoned the ether in his thesis in 1866 cause more problems, or was it a solution to the quantum conceptions proposed by Planck based on thermodynamics? Does the absence of ether in theoretical conceptions affect the entropy of the system and consequently the quantum information?
Okay, could you read that again? I'm sorry. Yeah.
Yeah, did the fact that, okay, so, and we can,
Okay, can I find it? I can read it in the chat myself.
yeah,
Okay.
let me copy just the text of it to you directly in the
Okay.
chat. Hang on one second. Here, you should get it privately in the chat.
Okay. I'm sorry, I don't understand the question. I don't recall any talk of ether or absence of it in Boltzmann's work on statistical mechanics.
Okay, then let's move on.
Sorry.
So I have a whole bunch of questions.
Okay.
I see we're out of questions from people in the audience, but I always have a whole bunch, and I usually wait
Okay.
until the questions that are being asked by the audience are done. Okay, so let me start with a couple of clarification. Actually, I have a question before I get to questions of clarification.
Okay.
So in the example you gave, I guess, Tim Maudlin's example of red balls and blue balls that may, apart from their superficial appearance, not have any meaningful physical differences that we could exploit to do work. So, the way that, that I understand Boltzmann entropy, showing up in statistical mechanics is, right, so we have some, so one way to approach it is to say that we have macro states defined by values of some macro variables, total energy, volume, number of particles, and I guess we could add to that list purpleness, right? Like how purple it is, either 0% purple, which we could call red, or 100% purple, which we could call blue.
Yeah, like if it's different colors, that presumably should be a macro variable.
Yeah, exactly. Right. We can distinguish macro states by how purple they are. And let's call that purple variable X. Let's say that macro variable is X. Then and then we can characterize the number of microstates in a macro state as some counting of microstates that share these macro variables, and in particular you could talk about the number of microstates that roughly share the same purpleness. And then the Boltzmann entropy is just k log that number, right? And then what you can do from that point is talk about how you could talk about various manipulations you can do on the macro variables, and how those those manipulations change the Boltzmann entropy, how they change the system's total energy. You can talk about heat, where you hold the macro variables except for the energy fixed, and study just how the Boltzmann entropy and the total energy vary. Or you can fix the Boltzmann entropy and study for fixed Boltzmann entropy how the energy varies as you change the macro variables.
Okay.
And for many of the conventional macro variables like volume, like particle number, and so forth, we expect to get a non-trivial relationship, in the sense that if you hold the Boltzmann entropy fixed and you vary one of these macro variables, you get a dependent change in the total energy of the system. And then from this, you can define like the thermodynamic potential associated with that macro variable. Sorry, this is getting very technical.
Okay, yeah, no, don't worry.
But for all of those macro variables where we get a non-trivial relationship and we can define a well-defined corresponding thermodynamic potential, we would say that those are sort of exploitable macro variables for the purpose of doing work. But suppose that one of our macro variables, let's say X is one of these macro variables, let's call it our purple macro variable, just doesn't have a non-trivial relationship to energy. You could vary the purple macro variable, and it just doesn't change. It just doesn't change U, the energy of the system. But of course, it could change the Boltzmann entropy of the system, right? Then I think this captures the sense of Tim Maudlin's example, where we have red and blue balls, and somehow letting them mix doesn't end up being something you can exploit for work. But suppose that there is a very small physical difference between the red and blue balls. Suppose their masses are just slightly different, or suppose they respond to some external gravitational electric field just slightly. And so there's like a little teeny bit of opportunity to make change.
Right.
Then we get a non-trivial functional relationship between the two. We can define a
Okay.
well-defined thermodynamic potential.
Mhm.
Would you say in that case that the entropy of mixing is fully meaningful in that case, in the Maxwellian sense?
Yes, so if you can differentially manipulate them.
Right.
Right.
So
And-
yeah, go ahead.
Yeah, and so, so I think that on the Maxwellian view, entropy is relative to some envisions class of manipulations.
Yep.
So if they are in principle differentially manipulable, and I include those manipulations in the class of manipulations with respect to which I define the entropy, then yes, there is the entropy, corresponding entropy of mixing.
Right. But of course, in some limiting case in which they're different only in these sort of physically not useful properties, like just their superficial color, then I can't avail myself of their mixing to do any kind of work.
Right.
But it seems like this is so it seems like this breakdown corresponds to some extreme limiting case, right?
Yeah, so this is what was originally called Gibbs paradox.
Right.
By
Of course.
Dewey
Yep.
and others. The idea was that entropy, like any other physical quantity, should be a continuous function of these parameters. Here's why I don't think it's paradoxical. We're not thinking of the entropy as an intrinsic property of the system. And actually, it's actually, if you think about it, a limit concept, because we define entropy in terms of heat exchanges over reversible processes. Of course, there aren't any reversible processes. What we think there actually are is, at least for macroscopic objects, processes that can approach reversibility as.
When you say entropy here, you mean like thermodynamic Clausius
thermodynamic
entropy,
entropy,
not Boltzmann entropy, right? Okay.
Right. So because Gibbs, Duhamel, when he found this quote paradoxical, was originally thinking about this in terms of thermodynamic entropy. So yes, in terms of thermodynamic entropy, why I don't think it's paradoxical. Entropy is a sort of limiting process, and it could be that as the difference gets smaller and smaller, to get closer and closer to get close enough to a reversible process, you just have to do it more and more slowly, right? And there is a very discontinuous difference between the limiting properties of very slow processes and things that are not going zero. So in one of my papers, one of the ones papers that I alluded to, and I don't remember which one, I imagine immortal ants, right? So imagine you've got ants that are crawling along at different speeds, and there's a little anthill and they go up, right? And so, and what's the highest, what's the highest point that an ant will ever reach? Well, it's height of the anthill for any speed greater than 0 and 0 for an ant that's not going at all, and there's nothing paradoxical with that.
Yep.
Now, should Boltzmann entropy be defined that way? Well, it depends on what you want Boltzmann entropy to do. I don't think that really Boltzmann, if it's meant to be have a close relation to, if the entropy concept you want is meant to have a close relation to thermodynamic entropy, which talk of how much work you can get out of the thing, suggests, then I think then yes, it's not paradoxical or bizarre that there's this discontinuous
Right. So you get my point here, right?
Now,
like,
yeah, but does it make sense for Boltzmann entropy to have that property? Well, what do you want your Boltzmann entropy to do?
well, I guess so. I guess to rephrase my point a little bit, you know, we get to decide in defining the Boltzmann entropy which macro variables we care about.
Right. Right.
And if we only include macro variables that have a non-trivial relationship to energy, then then we don't get anything that seems paradoxical. Every one of them will, by assumption, have a non-trivial thermodynamic potential, and changing it will be something that is manipulable and is connected with the ability to do work. If we're foolish, and decide to include some macro variable like purpleness that doesn't happen to have any connection to the ability to change the system's energy, then we're going to find that we have an ability to increase Boltzmann entropy, but in a way that doesn't track the Maxwellian understanding of entropy. So I guess one view of this is if we define Boltzmann entropy in terms of certain macro variables, where we could imagine some limiting process in which those macro variables lose whatever physical feature it is that lets them accomplish work, then there's this discontinuity that you talked about. Suddenly increases in entropy along those macro variables are now disconnected from the Maxwellian notion of entropy. But another view would just be that anything that becomes disconnected from work, we should just remove it from our specification of the macro state, and then the Boltzmann entropy should track the Maxwellian definition.
Right. Yeah. So if you want the Boltzmann entropy to have a close connection to thermodynamic entropy in that sense, then yes,
Right.
you should do that. On the other hand, you might have a different idea of what the Boltzmann entropy is supposed to do. So I think that when Popper and Albert and Shelley Goldstein are deploring the idea that entropy should be defined relative to state of information, they're thinking of it as something that tracks progress towards equilibrium. And even if these blue and red balls didn't behave differently and didn't have this nice relation to energy, I would expect that if they're just all jostling around, then if you start with a box with blue on one side and red on the other side and just let them jostle around, eventually they'll be more or less evenly distributed. And if I'm interested in tracking that, then I might want to include purpleness in my variables, even if it doesn't have, even if then the corresponding Boltzmann entropy doesn't have any nice close relation to a thermodynamic entropy.
That's a great, that makes total sense. There's a follow-up question from Jens about this. Jens, go ahead.
Just a brief comment on the quick exchange we had about the Gibbs paradox, just to kind of reinforce Wayne's point about that it's not paradoxical. So if you look at the Gibbs paradox in practice, you would actually expect some sort of continuous approach to that the mixing term, when you collapse the when you make the two gases asymptotically similar, you would actually expect the mixing term of the entropy to also continuously decrease. If you imagine, for example, you have semi-permeable walls or something that separate by charge, and you make the you make the charges of the two gases more and more similar, then you would expect some kind of stochastic failure of the semi-permeable walls to happen. And then I haven't done the exact math on it, but you would expect some sort of continuous. So it's really the discontinuity is then, on that view, really just another artifact of idealization. You often have the same way in which we sometimes approximate potential wells in quantum mechanics with those theta functions or whatever, and get this continuity there due to idealization. We get the same sort of thing in the Gibbs paradox.
I think that that's right. Yeah.
Okay, if there are no other audience questions, I have several more questions.
Okay, good.
Okay, so this is a somewhat a broader kind of a question, but I'm trying to understand exactly what you mean when you talk about two different theories we call thermodynamics.
Mhm.
And the comparison I'm going to make is to quantum theory.
Mhm.
Should we understand these different theories of thermodynamics in a way that's similar to thinking about, say, Bohmian mechanics and the Copenhagen interpretation or cubism? Is this, because of course there are often claims that for quantum mechanics, these are not in fact just different interpretations, but they're different theories.
Right.
Like Bohmian mechanics is a different theory from the Everett approach and cubism and GRW collapse theories. Now, arguably, some of those are more different from others because they make maybe more, explicitly different empirical predictions than each other. I'm just trying to get a sense, is there a way to think about your two theories, thermodynamics' two theories, as being like two interpretations akin? I'm not being super sharp here, but maybe you could clarify.
I understand. Yeah, so like things like Bohmian mechanics and the collapse theory, those are distinct physical theories. Like
they clearly are. Yep.
If the world is according the way it is according to one theory, it's not the way it is according.
Right. So we should throw that out.
Right.
Yeah.
So the analogy is with quantum information theory.
Okay.
So quantum information theory is basically a theory about how physical, it involves concepts like Alice and Bob are playing a game and here's their goal and here's the score of this game, right? And then you can say how, if they don't have any shared entanglement, this is the best they can do. And if they do have shared entanglement, here's how they can improve the scores according to a certain measure of entanglement. Okay, that's perfectly good theory, right? Even though Alice and Bob are not in their goals are not terms that appear in any fundamental physical theory. So Maxwellian thermodynamics is like that. It's a perfectly legitimate, and I said this to David Albert once. So look, once you've got the physics, be it quantum theory or classical theory, you can still ask what the physics permits agents with certain goals and means of manipulation and information what the system can do, right? And of course he says, yes, that's a perfectly legitimate endeavor. He said, I just wouldn't call that a theory. I wouldn't call that. Okay, fine. I don't care. I think in some of the papers, I called them different endeavors or modes of or
well, I mean, the language of resource theory, I think, is particularly apt here. The language of resource theory is particularly apt here because we have a pretty well-defined sense of what a resource theory is, and quantum information does behave that way, and so does the Maxwellian view of thermodynamics. And
a lot of people, and the dominant trend these days in people doing quantum thermodynamics is to import concepts and methods from quantum information theory and treat it as a resource theory. And
let me push
that actually is a return to the way that Maxwell and Kelvin et al. Thought about thermodynamics.
Well, let me push a little bit on this point a little bit. So of course I take your point that quantum information theory is pretty manifestly a resource theory, but if you look at, again, you compare something like, a hidden variables theory like Bohmian mechanics to textbook quantum theory. In a hidden variables theory like Bohmian mechanics, one has physics for underlying degrees of freedom. One is treating them according to some set of laws, one is using statistics on them, and one is trying to account for what systems are actually doing in the absence of observers. But textbook quantum theory doesn't talk in that language at all. Textbook quantum theory does talk about observers and what they can accomplish, right? Textbook quantum theory has the measurement axioms. It talks about what observers can do. I know that, talking about Alice and Bob and talking about games they can play has been sort of subsumed into quantum information theory, but when Einstein was writing, Einstein and Podolsky and Rosen were writing the EPR paper, they had in mind observers manipulating quantum states. I guess you could say they were already doing quantum information theory in that case, but it seems to me that like the textbook axiomatic approach to quantum theory has a lot in common with Maxwellian thermodynamics. It's a statement about what observers can accomplish, versus something like a hidden variables like Bohmian mechanics version of quantum mechanics, which is not about observers at all and is a statement about what the fundamental degrees of freedom are doing. I didn't need to muddy the waters with like GRW and stuff, but I think those two particular pictures of quantum theory, and I guess arguably they are different theories.
Right. So here's what I want to say. So basically, you can have operational theories where you say, okay, here's this class of operations that are going to be preparation procedures. Here's a class of manipulations that you can do. Here's a class of experiments you can do, and you talk about probability relations between preparation and operation and probabilities of outcomes of experiments. And so basically, I think the textbook quantum mechanics is an operational theory in that case, in that. And in an operational theory, it basically, if you stay at that, it's sort of agnostic about what's going on at the microphysical level. You raise the question is what could be going on at the microphysical level such that that you get these probability relations between preparations and outcomes of experiments. Okay, so then what it has in common with a resource theory is that it talks about operations you can do and things that agents, response to systems to manipulations and things like that.
And it also defines certain important quantities in terms of the operations that can achieve.
Right.
Yeah.
And what you add to get a resource theory is some sort of goals, things that you might want to accomplish.
Okay,
Right,
that makes sense. Okay,
right.
Yeah.
And talk about how certain resources let you accomplish those goals.
So that there's a sense in which there's a connection here between operational theories and resource theories, except that resource theories. Okay, that's very clarifying to me. But I feel like operational theories and resource theories are cousins. Like they're not. So there does seem to me to be like something like a bit of an analogy between operationalist textbook approaches, axiomatic approaches to quantum mechanics versus like Bohmian approaches, and this being somewhat analogous, maybe not exactly the same.
I think that's absolutely right. And in fact, there's this, as you know, there's this whole enterprise of characterizing quantum mechanics operationally in informational theoretical terms.
Of course, yeah, that's right.
The things that you can do. Yeah, so I think that that's absolutely right.
Good. Okay, that was very clarifying.
There's a close kinship between. I'm glad you raised this because I really hadn't thought of expressing it that way before. There is definitely a close kinship between characterizing an operational theory and a resource theory.
Good. That's really helpful. So I have one more question, and then I think we'll probably call it quits.
Okay.
And it's about Landauer's principle. So, so I've talked to John a lot about Landauer's principle, and I've read all your papers on it, including the.
This is John Norton, yes.
John Norton, yep, and I read your paper Shaken All Over, which was just extremely interesting and good, and it was a fantastic paper. So I just have a couple of clarificatory questions that I feel like this is a good opportunity to bring up because you talked about your approach to Landauer's principle in this talk.
It's too bad John's not here anymore.
He was here at the beginning, and I was hoping he'd stick around, but.
He was. I gave a talk. I gave an abbreviated version of this talk at the PSA in November, and he was in the audience there, and he didn't say anything. So he didn't object to anything I said. But,
So having like read his work on this and your work on this, I wanted to just ask a couple of questions that would be helpful for me to clarify like what's going on, because obviously you're making different claims, and his claim is that Landauer's principle doesn't hold. Your claim is that it does. But I think, so I'm not sure to what extent you've already talked with him about this, and I don't want to talk about someone who's not in the room, obviously, but you talked in your talk about people talking past each other. because they're using slightly different definitions and slightly different meanings of
Mhm.
things. So maybe I can formulate like this.
Mhm.
Rolf Landauer wrote his original paper on Landauer's principle. I'm very
Mhm.
familiar with this paper. I've read it. It is not a rigorous argument. It's a very
Mhm.
hand-wavy argument.
Mhm.
It's not exactly clear what the precise claim is or how he's
Mhm.
arrived at it. And I think, as John pointed out very neatly, there are all kinds of holes and problems with that argument that you can exploit to find counterexamples. So, and my understanding is that you basically accept that that's true.
Yes.
Okay. And what you did in the paper was to show that there's a very similar, or maybe similar is the wrong word because Landauer's original claims were a little bit hazy. You found a way to precisify a version of Landauer's principle.
Yeah,
And then prove it.
and I think, I haven't talked to them about this, that I think that what I formulate is pretty much what people like Charles Bennett have in the back of their mind.
Okay. Yeah.
And I've never seen the proof spelled out the way that I did, but I suspect that if you put it to Charles Bennett, he could, he could basically come up with basically the same proof I did.
Yeah. And I highly recommend anyone who hasn't read Wayne's paper, Shaken All Over. It's really good. It's really clear. So, but your approach, it relies on this fundamental assumption of thermodynamics that you stated in this talk, that the best ensemble, the distribution we use is the kind of canonical ensemble, which is of course something that John does not assume. He's thinking more generally. But based on that assumption and based on the precise way you define some of these thermodynamic quantities and the fact that you're working sort of at a probabilistic level, that you're making a claim that Landauer's principle holds for appropriately defined quantities in a probabilistic sense, an average sense.
Right. Yeah.
But that it can, in principle, if you don't take on all of those premises, it could, in principle, be, strictly speaking, be violated.
Yeah. So the theorem, theorem, like so many theorems, is a form of if-then, right?
Right. Of course.
So,
yes. Absolutely.
Yeah. I stand by the conditional.
Right. Like I guess I'm trying to find is a way for it seems like John's arguments seem correct in the sense that he has clear counterexamples, and of course your argument seems correct. And I'm trying to understand in what sense you can both be correct because you're starting from somewhat different.
Yeah. So I haven't really talked to John recently about all this stuff. I started thinking about. I didn't really delve into the Landauer principle literature until a couple summers ago. I think it was probably the summer of 2020 when I was working on writing that Oxford Research Encyclopedia article. And I thought I had to have something about Landauer's principle, right? For grad students in the audience, never agree to write a review article or a research encyclopedia article before you have tenure, because it literally is reading 14 papers to write one paragraph. Right. So I basically printed out all those papers and read them in sequence, and as a consequence of thinking about that, came up with my paper. And so it's not clear to me what at this point John and I don't do or don't agree on. Right? And I sent him the paper before I sent it to the BJPS, and he said he expressed a lack of interest in reading yet another proof of Landauer's principle. And I would actually like to sit down and talk with him at some point, but yes, this was written in the summer of 2020, and then
who remembers that?
We had a couple of years in which no one was talking to each other face to face, right?
Right.
So I would like to sit down with John and figure out what we do and don't agree on. So one thing that John could take is Landauer's principle is indeed a consequence of a probabilistic version of the second law of thermodynamics, and so doesn't help at all to exercise Maxwell's daemon. I think if you could agree to that, but it actually does follow, right? if you could agree to that, then okay, we're fine. And then he would say, yes, but it doesn't matter because if you take into account everything involved in the system, including the outside influences that might be manipulating it, then there's always an entropy increase that totally swamps the Landauer bound. Now, I don't think he's established that. I don't think his arguments establish that, but one could say that and say, yes, I accept Landauer's principle is correct, but kind of pointless because we're never going to even get close to the Landauer bound. Now, but one thing that I do want to talk to him about is that, so I'm talking about probability distributions over state of the system, and that can include cases where you say you've got a ball that's determinately in one box or another, and you just don't know which. So you've got a certain probability for being in this box and a certain probability in that box, right? Now he takes probability distribution, at least initially in his earlier papers, takes the probability distributions that you're dealing with to be referenced to a temporal ensemble. So that the probability associated with a region of phase space is the long run amount of time that it takes to spend, right? And that's why in my Landauer theory principle paper, I explicitly say I'm not doing that. Because in that case, like if you've got a ball that can be in one box or another, then with non-zero probabilities with each, that isn't going to correspond to the long run amount of time that it's going to spend in each box, because it's either stuck in one box or the other one. And if that's how you're thinking about these probabilities as temporal ensembles, then my proof just doesn't work.
Yeah, okay. Yeah,
so it might
that's
be
helpful.
that he's just, and that underlies his talk of illegitimate ensembles. Like an illegitimate ensemble is one where you're imagining an ensemble of things that don't correspond to temporal distributions of a single system. So it might be that he's right if you think if this the probabilities be interpreted in that way. But if you're thinking about dissipation as loss of ability to extract work, then that's not what counts. What counts is knowledge of the system.
This is very helpful. So we're just about out of time, and I know that John isn't here, but I feel obligated to say that wherever you are, John, you've been a very good sport because we're talking about it. But yeah,
so hopefully at some point, John and I will have some time to sit down and talk about these things and figure out what, if anything, we still disagree on.
Right. It would be incredibly
it might be
to hear that.
It might be that there's more agreement than appears.
Yeah. It would be extremely elucidating to hear that. Anyway, we're out of time. I want to be respectful of everybody's time. This is our last talk in the seminar series for this semester. Like I said, we'll reconvene in the fall, so stay tuned for an announcement. I want to thank Wayne Myrvold so much because this was a great talk and a great discussion and Q&A. So thanks again, Wayne. And
thank you for all your questions. You've allowed me to clarify my thoughts on some things. So thank you, and I think everyone else who asked questions has already gone, but thanks to them too.
Yeah. Thanks to everybody for joining us, and have a wonderful summer, everybody.
All right. Take care.
Bye-bye.